Hi everyone, this is Wen. In today's video, I'm going to go through the code that provided by Pavel Nuniak, which is going to implement a neural network in Cuda. And I think this is a really good code, and I hope to go through this code and then give you a better understanding on the implementation of neural network in Cuda. So this topic will be divided into two videos. In the first video, I'm going to go through some basic classes as well as some basic layers, and in the next video, we're going to wrap up everything, and hopefully by these two videos, you will get better understanding on how to implement neural network in CUDA. So let's take a look at the code, but before the code, I hope to give you a highlight or overview of the structure we're going to implement. So we're going to implement a neural network with 4 layers. You can see we have a linear layer, we have a ReLU layer, we have a linear layer and sigmoid layer. So this is overall structure of neural network we're going to implement. So first of all, let's take a look at the main Cuda. So basically in the main method, we're going to have a neural network object initialized, which is going to be able to add layers. For example, we can add linear layer, we can add ReLU, we can add sigmoid, we can give different names to this layer, as well as we can put some arguments into the layer. And in today's video, we are going to cover the ReLU activation and the sigmoid activation and other basic classes, and the linear layer I will include in the next video. And so for this argument shape 230, the shape is just an object of 2 dimension. We can take a look at that soon, but let's set it aside and don't care about what does this mean for this moment, and focus on the ReLU and sigmoid in this video. So from after we define the layers in the neural network, we're going to do the training process. You can see we're going to have 1000 epoch, and in every epoch we're going to loop through all the batches, and for every batch we're going to do the forward, and this neural network object will have a method called the forward, which is going to basically loop through all the layers and do the sequentially forward, but every layer will be implemented by the device which is in the GPU, which will be very fast compared to the CPU. And then we're going to do the back propagate, and this will be do reversely from the last layer to the first layer. So this is kind of a reverse way. And the data is different. First one, we're going to take the n-1 columns as input, and the second one, we're going to take the one last column in the batch, which is going to be the label to help us to do the backward propagation. So this is how it does. And then we're going to calculate the cost, and in the end we're going to take the accuracy and output the accuracy of the overall training. So this is a big picture of implementation everything. So first of all, let's take a look at the shape. This is a shape class, which is basically defines 2-dimension object, which is xy, and in the Cuda file, which is going to be implement this declared method. And let's take a look at matrix. I think this is most basic and very important class in this whole project, because everything is based on the matrix, right? So in the headers file, there are many variables and method declared. So as you can see, we have the device allocated and host allocated. These two flags, which is going to tell whether for this object, whether the device has been allocated memory or the host has been allocated memory or not. And then we are going to have the allocate CUDA memory methods, as well as other method were declared in the headers file. So for here, we are going to have the data device and data host, which are both are going to be used a shared pointer, which is a smart pointer in C++. And the good thing about shared pointer is going to count reference for us and automatically deallocate the memory when suitable. So this will be used for the data on device and data on host. And then we declare several other methods as well. We declare the allocate memory, we declare the allocate memory if not allocated. And then we have the cost host to device, copy device to host. So this method will be implemented in the Cuda file. And then we have other two operators which are going to have the overflow. You can see the second one is a constant. Let's take a look at the matrix class. So in the matrix class, we're going to implement all the things that defined declared in the headers file. So we're going to have a matrix constructor, which is going to take two parameters, which is x dimension, y dimension, and then we use a column to include an initialization list to initialize the fields that declared in the matrix header. So you can see this device, data host, and shape and allocated or host allocated is defined in the headers file. So this one will help us to initialize the fields when we create the object. And then we can also parse a shape object, which is going to have x, y dimension instead of separately defining. And then we're going to allocate the Cuda memory, and this is method in the matrix class to allocate the memory for the Cuda. So what you're going to see, because what we introduced, it will use a shared pointer. So we define a shared pointer, and which is going to have two arguments. And the first one is going to be the allocated memory to the shared pointer. So this is going to be the device memory. And then we are using a lambda method to help us to declare the delete operator for the shared pointer. So as we discussed, the shared pointer is going to be deallocate the memory whenever needed. So by default, the delete function is going to be delete, because most of case the delete will happen on the host. But here, because we are doing on the Cuda, which means we are going to do on the GPU, so we need to use a Cuda free instead of delete. On the other hand, when we take a look at the allocate host memory, which will be quite similar to the previous one, but only difference is that we are going to use a default delete operator when we do the deallocation. So this is the difference. And then we are going to, after we allocate the memory, we are going to set the device allocated to true and host allocated to true. We also have the method to allocate the memory, which is going to call the two methods as above. And then we also have allocate memory if not allocated. So basically we're going to check the flags and see if they're already allocated or not. Otherwise we will call the allocate memory method. And we also have the method to copy the host to device and copy the device to host. The only difference is what we're going to use the same Cuda memory copy method. The difference is the direction. One is a copy host to device, one is copy device to host. So this is the only difference. And then we have the operator method, which is going to be implemented. One is a constant, which is going to return the data by the index. So this is a matrix method. And let's take a look at the neural network layer. So this is kind of basic class we're going to define, because we're going to use a polymorphism, which is going to have all the layers to inherit this basic layer, neural network layer. So we are going to have a name for this layer, as well as we have the constructor, and we also define the method for the forward and backward. And basically we have the different matrix as inputs, as well as a learning rate. So today we're going to go through the sigmoid and ReLU layer. Let's take a look at the sigmoid first. So before that, I hope to show you something about sigmoid layer. So basically, this is a formula how to calculate the sigmoid function. So basically, every element in the matrix will be calculated by this, and then this will be populated into the result in the output matrix. So on the other hand, the backward propagation, sorry, the backward propagation formula is like this. Basically, we're going to take the propagated derivative from the last layer, and then we're going to times this formula, which is going to be consist of the sigmoid function, and this will give you the back propagation results. So let's take a look how it works and how it implemented in the sigmoid activation layer, which is going to inherit the neural network layer. And we have several variables declared. One is matrix A, which is going to be the layer's output, and we have layers inputs, which is going to be the layers matrix Z and matrix DZ, and this DZ will be used in the back propagation. So basically, this is a very clever way to implement, because every time we want a single layer to be one object, and every time we can keep the result in this matrix, and after maybe batch or after every time learning, we are going to update this same object or this same matrix, and in the end we're going to get a result from the maybe 10,000 epochs. So let's take a look at how we implement in the Cuda's file. So in the Cuda's sigmoid function, we're going to have the sigmoid method declared first, so which is exactly fit what we just showed, the formula, which is going to be 1 over 1 plus exponential of the minus x. And then we're going to have the sigmoid activation forward kernel declared. So you can see this global or device. The device just means its code can only be called on the device, but if we do this global, we are able to call this kernel's code from the host. So that is only the difference. So while we declare the sigmoid activation function, we're going to have the forward with several arguments. One is z, one is a, and z dimension of x and z dimension of y, because z is the input and a is output. So we are going to calculate the index for the current thread first, because every thread will do the same thing, but we will need to know which index we're going to access and which index we're going to write in the matrix. So we will do the sigmoid function on the corresponding index for current thread, and then we're going to write the result into the output matrix for this layer. So the same thing when we do the back propagation, we are going to have the z, we are going to have the dz, as well as we have dA. dA will be a propagated derivative from the last layer, which is going to be the propagated derivative we're going to times with the local derivative. So that is how we do that. You can see the dA times the sigmoid function times 1 minus sigmoid of z, which is z is the output of this of the forward propagation. So this is how we calculate the back propagation, and we'll save it in the dz. And then we're going to have the function constructor, which is going to be given a name for this layer. We also have a deconstructor, and we have the forward method, which is going to be called from the host, which is going to initialize which is going to call the kernel, the forward kernel, and give the correct block size and the number of blocks. You can see the block size is fixed to 256, and then we're going to give several arguments. For example, like the a device z device.get and a device.get, which is going to get the value from the z and a, and then we have the shape of the x z. The same thing, the back propagation, we're going to call the back propagation kernel in the similar way. But in this time, we're going to give the derivative propagated from the last layer as well. So this is the only difference from the forward propagation. So let's take a look at the ReLU layer. And ReLU layer is basically to inherit the neural network layer again, and which is going to have several variables. A is the output, and z is the input, and dz is also the input for the back propagation. And we have the function constructor and function deconstructor, and we have two methods declared. And let's see how they implemented in the Cuda file. So basically, in the Cuda file, we are going to implement the kernel. The forward kernel will take the z, a, and z x dimension and z y dimension, because a is output result and z is the input result. We are going to do the f max f, which is on the input with the corresponding index for current thread. And this method, f max f, which is going to give us the larger float point arguments, which is whichever is greater, either this one or 0, will be returned by this result, which is going to be exactly what ReLU function do. And then in the back propagation kernel, we are going to give it not only the arguments as below, we also give it a propagated derivative, which is going to be the dA. The dA will be used in the calculating the final result, because before that I hope to show you how to calculate the forward propagation as well as the back propagation for ReLU layer. So as we said in the previous one, we choose whichever is greater, because x, only when x is greater than 0, we are going to set a value as x for the ReLU function, otherwise it will be 0. So this is why we choose whichever is greater in the forward propagation. For the back propagation, we're going to check whether the x is greater than 0 or not, and this one will depend on dA. The dA will be this one will depend on x, because we're going to check the result from the output layer, and then we're going to decide whether it's 0 or dA. So this is a way how we calculate the forward and backward propagation for the ReLU layer. So basically, you can see from here, we're going to have this dA, which is going to be the derivative the propagated derivative from the last layer. And we also have to check whether the output of current layer is greater than 0 or not. If it's greater than 0, we are going to say, oh, it's equal to the propagated derivative. And there is no local derivative for this case, so only the propagated derivative will be considered, whether depends on the output of this layer. So you can see that the index will decide whether we choose 0 or the dA. So this is the difference. And we also have the function constructor for the ReLU layer and the deconstructor for this layer. We also have the forward, which is going to be called by the host, which is going to initialize the kernel with the proper block size and number of blocks. And then we have the values as arguments for this method. And then this will be the forward propagation. And then we have the back propagation, which is going to be similar to the previous one. Only difference is we're going to propagate a propagated derivative from the last layer, and then depends on the output of this layer, we're going to decide whether we'll choose this one or 0. So that is how we do the backpropagation from the ReLU activation layer. I think we can take a look at the neural network layer as well, because this is also very important. This one, we are going to have several method declared and variable declared. As you can see, the y and dy, and basically we have the cost function, the cost value, or the initialize value of the cost. And then we have the neural network and the deconstructor for propagation and backward propagation. In the next video, I will discuss more about the cost function as well as input and output of the whole overall neural network. But now let's take a look at the forward and backward method for this neural network. So if you take a look at forward and backward method for the neural network object, we're going to basically loop through all the layers in the current neural network object. So we're going to do them sequentially, one by one. We're going to call the forward method in each layer, because every layer is going to inherit the basic neural network layer, and then each of them will have this forward method. And the same thing for the back propagation, we're going to calculate the error first. And this will be discussed in the next video in detail, but for now we only care about this part, which is going to do the reverse iterator. We're going to check the R beginning, which is going to be the last layer, and to the first layer we're going to do this again to do the back propagation, and we'll propagate error from the last layer to current layer, and we propagate the learning rate as well. But as you can see, some of them actually don't need the learning rate, only the linear layer will require that, because the linear layer has to update the weights of the edges. So that is only difference. So I think that's pretty much for today's video. I will keep working on the next video, and hopefully by next time we will wrap up everything, and you will have better understanding of how to implement Cuda with the neural network. Thank you so much for your time, and hopefully you can enjoy this video. Until next time, happy coding.